charged particle or particles moving in an electromagnetic field. So we have seen that an interesting space curve, the helix, occurs in the model of DNA. Another notable example of a space curve in science is the trajectory of a positively charged particle in orthogonally oriented electric and magnetic fields. So if you have the magnetic field going, this is the B field going up like that, and the electric field going sideways like that, what ends up happening is you're going to have a shape that looks like this. This is, depending on the speed, you're going to have a shape that looks like this, like that. And this is a cycloid, like that. And another shape is you can have it like this, going like this. This is a trochoid, which is actually a more general type of cycloid. So anyways, basically you have this equation right here. This is R for this one here. This is typical trajectories like this. This is where the t minus sine t. You have 1 minus cosine t for the y component, and then t is the parameter t, I guess. And this graph is based on t like this, and this is a trajectory of it. Yeah, this is a trajectory in space, and then with E and B fields going perpendicular like that. So that's interesting. And then there's the this is the other formation depending on the speed of it. We'll get to that in a bit. So this is t minus 3 over 2 sine t. Again, these could be different, but this is just an idea of some typical values. And there's 1 minus 3 over 2 cosine t for the y, and there's t variable there. So a motion of a charged particle in orthogonally oriented electric and magnetic fields. So depending on the initial velocity given the particle at the origin, and yeah, so you have the particle at the origin somewhere. So it could be like this. Yeah, unless it's going this way. Yeah. So you have the path in the origin like that. There. Yeah, so depending on the initial velocity given the particle at the origin, yeah, and the path of the particle is either a space curve for its projection on the horizontal plane. This is a projection right here. So this one's a projection straight down. This is just at all different angles there. But it's a projection straight down. This is a projection straight down as well, like that. So it's a projection straight down. Yeah, so a space curve whose projection on the horizontal plane is the cycloid we studied in my earlier video, and I'll put out some screenshots here, and there's a link to my earlier video. Or B, a curve whose projection is a trochoid. See exercise 4. So I never covered it before in my earlier chapters, but I will do that at the end of this video. So this is a cycloid. So recall a cycloid. Cycloid is formed by tracing the position of a point on a circle as it rolls. So you have a circle right here. As it rolls, and then you keep tracing that point, it's going to form like this. And it's on the point, so it never goes below that. But a trochoid is just a more general version of the cycloid. So the trochoid is formed by tracing any point inside on, hence a cycloid, or outside a circle. So if it's on, it never actually touches the bottom, so it's basically like this. Yeah, like that. If it's on it, you get a cycloid. And if it's outside of it, you're going to have a loop. So it's outside of it, and as it rolls, it goes out. It goes backwards as it hits the bottom, and then it goes like this. Yeah, so it actually loops around like that. So it's pretty cool stuff there, and I'll show you some illustrations. And I think I have some illustrations. All right, yeah. So here's the trochoid Wikipedia page. This is illustrated in animation form. So there's an animation right here. There's a cycloid. It's at the point like that, and it goes straight on it like that. So pretty cool stuff like that. Yeah. So that's a cycloid, just tracing a point on it. And we go to the next one. Next one, this is a trochoid, but they call it a prolate trochoid, which is basically extending past it and loops around like that. And then the other one is a curtate trochoid. This one doesn't, it's inside the circle, point inside. So it goes like that, never touches the bottom. There's no sharp edge or loop. So it's pretty cool stuff. All right, let's continue back. All right, so we have this. So note, some computer algebra systems provide us with a clearer picture of a space curve by enclosing it in a tube. So here it's, this one right here, it's hard to tell how it's looping and so on. But if you put in a tube, you can see it in 3D, which form it's going. So so such a plot enables us to see whether one part of a curve passes in front of or behind another part of the curve. And the figure below shows the curve of B as rendered by the tube plot in tube plot command in Maples. It's just a mathematical program. Just a pretty advanced mathematical program and graphing setup there. So this is the tube here, and this is the graph, and they put a tube there. So now you could see that it loops around this way. Or if it's starting from the origin, if it's starting from the origin like this, it loops around like that. So yes, pretty cool stuff there. And that's in 3D, so you can see in which one is overlapping, which side. And here are the graphs in GeoGebra. So there's the link there. Let's open this up. So it's going to be a pretty big graph right here. I'm going to close some stuff here. Alright, so we close some stuff, see if it's loading, and while it's loading, let's go back here. So here's the graphs in GeoGebra that I put in. So note the graphs are plotted when z equals 0. Still match those in blue because of symmetry. Again, this was actually before I realized it's a projection. I'll just erase these. This is, yeah, don't need to write that. So basically, the ones at z equals 0, that's just a projection. Yeah. Cycloid XY, that's a projection, yeah, because it's, the calculus book already said that. Yeah, so it's, so basically we have the trochoid right here. I put those parameters in. I put the components, and then I made it from t, made from 0 to 12 pi, just whatever until a decent setup there. Cycloid, and there is a cycloid projection on the xy plane, where the z is 0, and there's a trochoid on the made z equals 0, z equals 0. So there's the cycloid, t minus sine t, 1 minus cosine t is again same thing, but then I set up the 0. And here's the graph how it looks like. So it looks like this. I put them both together, and you can see it like that, and you can see them plot them out separately. There is the cycloid one. If you project it straight down, there's a cycloid shape. And the other one, if you project this one straight down, you get that trochoid setup there. So since there's no tube command, and also this also is interesting as well. So it's still loading. It's not loading. Okay, there it is. See the algebra. Do I have the algebra? Okay, the algebra setup is pretty complicated. So I'm going to go right here. I'm going to go all the way across here. And so this is the cycloid. I will unhide this one here. So there's a cycloid like this. And then you can see the projection straight down. And there it is in 3D like that. So again, it's hard to see, but you can see it loops around like that. It's decent. And then there is, that's a cycloid. Let's go to the trochoid. So there's a trochoid, put it straight down. So that's again, that's exactly what we get. So there's a looping around effect like that. And so since there's no tube command in GeoGebra, so I can just put tube, make it a tube similar to this one. No tube command, but instead, since there's no tube command, I use the surface command via Grok AI. So just using, I said, make me a tube command or tube setup or similar tube setup on GeoGebra to generate a circular cross section of the curves. There's what it made up for me, and basically the whole idea is to simplify it. It looks giant. But basically it takes these curves. For example, here is the, I'll do the cycloid. Actually, I'll do the trochoid. There's a trochoid. There's a trochoid surface. And I'll do the trochoid and the XY. So what it does is I'll take that curve, the surface. So basically trochoid surface, and it puts these in. But I also included this setup here, what Grok AI added. This 0.2 cosine u, it added a third parameter, and this one is just literally just going from 0 to 2 pi, where, yeah, 0 to 2 pi. All it is just making a circle around it, cross section. Again, this is all super complicated. I didn't want to, it's not that complicated if you break it down, but anyways, it's outside of this video. And again, there's this shape there. All it does is create a circular cross section. I do this in another exercise. It's in a bit simpler one, but that one was just super advanced. So there it is, and it's notice all the calculations being put into it, and you can see it loops at the bottom and up, loops at the bottom and up. And if you scroll all the way in, you can see you could kind of see that cross section circular surface that it made. So basically, what it does is at every point it adds another parameter, and it loops around in a circle. And yeah, so there's it's a circular setup like that. But I think I made the X and Y axis not in sync, so they're a bit out of shape. But anyways, it's just too slow to figure this out or make it a bit nicer. But anyways, that's the general idea. So that's that. And then again, I added the Grok AI added this extra term right here. Whoops. Yeah, this added this extra term, the U, to every single one, and it also puts it out like there. So it adds all these U parts right here, and this is all just to make a cross section circle surface. All right, and that's what we have here. Yeah, so we have this one is for the cycloid. This is a trochoid, and I want to do it right here. just for completeness. Go back to the algebra. Okay, a lot of times a bit slow. This is a giant calculation. There it is. This cycloid and then cycloid surface. And yeah, actually, I do want to make this. Here, I'll see if it makes it better. What I'll do is I'll do the settings. So I'll make this -4, just so that it's all the same size. This is -4 to 4, -4 to 4. So it's all the exact same scale. Okay, so it scales up like that. Yeah, so you can see how it makes it a circle. It makes a circle from at this cross section, and I'm not sure how it changes that well. But anyways, so that's that. I'll make it even a bit more. Just so it's exactly the same length there. So this is the Z 0 to 4. How does that work? Yeah, to make it exactly the same size, I'll scale up one more try. I do want to make this nice. What I'll do is 0, x0, 10, 0, 10, 0, 10. Okay, let's see what happens now. So it's always the exact same. Yeah, so it's a pretty cool shape there. And this is the cycloid one. That's the thing. It's a cycloid under the trochoid surface. And this is pretty cool stuff anyways. Yeah, so that is pretty cool there. I just made sure that the scale is the same thing. So yeah, it is like a twisted setup there. Pretty cool anyways. And there's the setup there. Alright, so anyways, let's go further. And this one here, we're going to look at the physics of charged particles in electromagnetic fields. And this one, it's more for my sake. I just want to learn a bit more. But again, this is from my calculus book. It says, for further details concerning the physics involved in animations of the trajectories of particles, see the following website. So included link right here. This one right here, note that to run this website, you'll need to run Java applets, which you apparently all the new browsers don't have anymore because of a security issue. But you can download a browser extension that, like this one, I downloaded it and it works. So this one here does not have this anymore. So this one, if you can see this, it means your browser cannot run Java applets. Please upgrade to a Java capable browser like Netscape 3.01 or Windows 3.1. So again, this is like decades ago. I'm gonna download this quickly. It's on my laptop. I had it on my other one. But anyways, when you download it, it looks like this, and we'll do some testing out. So this is magnetic field going up on the Y, and there's the electric field going this way, and then the shape goes up like this. If you have just if you have just the magnetic field, it just goes in a circle or something. Oh, actually, this is graphing T. No, that's yeah. If you just have it magnetic field itself, it might just go in a circle. So anyways, so that is what we have there. I'm gonna go download this quickly. Add the Chrome. I'm using Brave browser, but it should work. Yeah, but they're both Chrome. Okay, I'm gonna add this quickly. Add this, and let's see if I can run this. Oh, it's downloading. Alright, so I downloaded. It should run now. Let's see if I go right here. And so on. There it is. Let's go over, pin this, and go here. Charged particle motion. I just want to show this. This is a pretty cool site. Apparently, it's hard to do. There isn't any modern sites that do both of these on there at the same time. Besides, like, some advanced ones, they either have to pay or sign up and all that stuff. Okay. Enable for this domain. Alright, here, it's loading up now. It took a while to load up, but anyways, there's the loading up right here. So it's charged particle motion, and then there's a bunch of stuff here on what it does. And again, I don't want to, I don't want to go through it all. It basically uses Lorentz force on, Lorentz force acting on a point charge. Q is given by this equation. It goes over the equations. I'm just gonna go start right here and see what happens. I'm gonna zoom in. So it's going up, and I think it's gonna go into cycloid. Let's keep going. Yeah, so let's keep going. See what happens to this shape right here. So again, it's doing a lot of mathematics. I think it's just going to be a cycloid in this case. So again, depending on the speed and so on, you're going to get different setups. So there's a cycloid particle going in an electromagnetic field. It's from like decades old software. But anyways, I want to illustrate that. Okay, stop. Okay, it doesn't stop. There's a stopping. And so, and again, you could play around with it, and so on. You get a cycloid, and see if you can get the trochoid. So anyways, this is from the other link that they added here. And it's pretty extensive, but it's a bunch of experiments. But I do want to read this for completeness. And also, so again, I'm going to read this all, and then some of it I'll need to review later. But again, this is for my own sake. So, single particle motion in electric and magnetic fields. So the following photographs were made in the Physics 180E undergraduate 180E undergraduate laboratory course in plasma physics by Professor Rainer L. Stenzel. They are designed to demonstrate the single particle motion in electric and magnetic fields. A weak electron beam of 100 electron volts, and then from 1 to 10 milliamps, is injected from an oxide-coated cathode. So the cathode is the positive end, I believe, and then the anode is the negative. Into a low-pressure 0.2 millitorr. It's like vacuum argon gas. The beam partially ionizes the gas, so you get the free charges. The background plasma has a potential close to that of the grounded chamber wall. The beam electrons are accelerated by an electric field mainly concentrated in the cathode's sheath. Interesting, and the trajectory of the beam electrons is visible due to light excitation when the beam electrons collide with argon atoms. No visible light is produced when the electron energy is below 10 electron volts. Yeah, that's EV electron volts. Several basic phenomena can be inferred from the following pictures. These were taken with a Rolleiflex camera, 400 ASA, black and white film with up to 1 minute exposure time. So again, it's pretty ancient tech here. So this is a plasma setup there, basically just a bunch of electrons. Figure 1, a 100 electron beam is ejected into a neutral gas or argon without applying external electric or magnetic field. So there's no electric or magnetic fields. It looks like this. Interesting how it dips in like that and then pulls it up. The beam starts very close to the cathode, indicating that the electrons acquire their full energy in a very thin cathode sheath. Thus, the self-produced plasma acts as an anode, so the negative side. The initial beam converges indicates concave equipotential surfaces near the cathode. Interesting. I gotta read up on this. Near the cathode, presumably due to a radial density gradient, the beam scatters by collisions and beam plasma instability. So interesting. So beam plasma is unstable and expands out, but it looks like it wants to compress again. So that's pretty fascinating. And now here is figure 2. So, did I miss figure 2? All right, here, yes, I actually did miss figure 2. And here's the actual original site here. Here's the original one here, single particle motion. From the UCLA website right here. And yeah, so I just basically copy and paste the text and the images, and because I think it's very valuable information. So the beam is ejected against a negatively biased grid. When the bias voltage is slightly larger than the cathode voltage, most of the beam is reflected, but a few electrons are transmitted, so it goes through. Note that the equipotential surface near the grid is not a plane, but a convex. Interesting. So it's this one here. I think is that what they're talking about here? It's a bit convex, not yeah, it's a convex. This causes an angular spread of the reflected electron. So yeah, there it is. It spreads outward like that. Electrons in the center of the beam are normal to the sheath and can pass the grid when their energy exceeds the potential energy of the sheath. So it goes through it like that. Fascinating. And then going further, yeah, this is yeah, this is. Oh, actually, I put this above this. Okay, this is figure 1. This is figure 2. Let's put this, let's fix this up quickly. All right, and copy and paste this right here. All right, so that's that. And now the next one is right here. So beam injection against a very negatively biased grid, which reflects all electrons. So it's because electrons are negative, hits a negative, and it reflects a lot. No dark sheath near grid, where the electron energy is decreased below 10 electron volts. This is a dark sheath near the grid. I think is this what it means right here, the dark one. I'm not sure what that is. The electrons stagnate in the dark sheath and form a convex equipotential surface. This causes the reflected beam to be highly divergent. So convex. So I think it's shooting outwards like that. Or is it actually talking about this one here? Stagnates here, so it's concave surface. And I'm not 100% sure, but this is pretty cool stuff here. And then here's the loop right here. So this is a 100 electron volt 100 electron volts electron beam injected perpendicular to a DC magnetic field, so direct current magnetic field, so not alternating current, just direct current magnetic field, and this is perpendicular to it. So if this is shooting like that, so the magnetic field is either this way or this way through it, and it's using an electromagnet, DC magnetic field. The sense of the cyclotron orbit implies the magnetic field points into the plane, so into the plane like this. And that is the sense of it. I think that's just the way how it looks like. And the beam energy and the cyclotron radius. From the beam energy and the cyclotron radius, the field strength can be calculated. Note that the beam light weakens with propagation distance. And this is the cyclotron. Basically, I think it just means this right there. Again, I don't have time to double check everything because I wanted to include this for my own research during this video making. And I think there's 12 images. I'm going to go over some of them. Again, these are all fascinating. So figure 5, a low energy beam is injected across a magnetic field as in figure 1. As in figure 1. There was no magnetic field. So this one here is injected here. This one has no magnetic field. And this one, I think it might have made a different one. Okay. So, as in, it might be saying figure 4. Figure 4. I'll put the... put the code fig 4 question mark. Okay, because that's this is because this is it looks exactly like that. Well, it's different, but it's the figure 1 didn't have a magnetic field. Figure 4 did, and it looks like similar. So the cyclotron radius is decreased. Note the dark gap between the cathode and the beam onset. In this sheath region, the electrons still have insufficient energy for light excitation, and that's just right here. So they don't have enough energy to excite light in the argon gas, and then so again that's what it means there. So again, I think that's what it's talking about, this convex part right there. I think that's what they were talking about. Anyways, so that is fascinating stuff. So this one's less energy. All right, going further, a low energy beam is injected against a decelerating electric field. Interesting, and I think it's perpendicular as well. As the beam energy falls below 10 electron volts, the light emission stops. So it doesn't have any more emission past this. It doesn't excite the argon atoms anymore. The beam and current continue to flow through the dark region. So the beam and current still goes through, but it doesn't have enough energy to excite it. So that's pretty cool. That's an electric field. All right, and going further, at neutral pressures, the injected electron beams rapidly spreads. This is at high neutral pressure. So this is at high pressure of the argon gas. I believe that's what it means. The electron mean free path can be inferred from the beam decay. And again, it's like after this point, it just spreads a lot when not pressure is high, because it's hitting a lot of the argon gas. So here's a figure 8. Electron motion in crossed electric and magnetic fields. So I think what it means is perpendicular ones. You have electric magnetic fields in perpendicular setups like this. I think that's what it means. And then there's our trochoid. The trajectory of a cycloid is actually a trochoid. Superposition of a circular motion, a constant drift to the right. This should be a trochoid. A cycloid is a specific type of it, I think, or trochoid, I think. Or it should be just more general trochoid. I.e. a superposition of a circular motion, a constant drift to the right. The cyclotron orbit implies a magnetic field direction into the plane, so it's going into it. So this means going in. If you draw a dot like this, going into it. No, actually that's going out. Into it would be like this. Yeah, this is going into the page. Think of it as an arrow. I think that's how it is. Into the page. So here I just quickly googled magnetic field into and out of page sign. Let's see which one is into and out of it. Yeah, out of page, into page. Yeah, that's the X. And you can think of it as like the this is the tip of an arrow, and this is like the bottom of it. Okay, so this is into the page, and yeah, so into like that. All right, so that's into. I'll just erase it. So yes, okay. Implies a magnetic field direction into the plane, and E cross B drift implies the electric field points downwards. So yeah, so this electric field is going down, E is down, and then into the page is the B field, or the magnetic field. Typically they call it B. Yeah, so the down and the other one like that. Interesting. So it's saying that the E going down implies the drift. This is what's going down around where that electric field is. So if it's pointing down, electric field is going down. I mean, if it's going down, electric field is going down, possibly. From the known beam energy, the field strengths can be obtained from cyclotron radius and guiding center drift. So you can calculate the beam energy and so on. And there's a drift. So that's pretty fascinating stuff. There's an electron beam spread there. Here's some more cool stuff here. So mirror reflection of a weak electron beam in a non-uniform magnetic field. The beam is injected oblique to the field lines, so at a different angle, which converge to the right due to the adiabatic invariance or energy and magnetic moment. The parallel energy is converted into perpendicular energy, at which point the particles reflect. Alternatively, the parallel motion is decelerated by the repelling force of an increasing magnetic field. So again, I'm not 1000% sure, but it looks like it's going like this around there. But it says there's a mirror. Mirror reflection of a weak electron beam in a non-uniform. So it's like a reflection there, and it goes backwards. Yeah, so it goes like this and hits backwards. The beam is injected oblique to the field lines, will converge to the right. And this is due to adiabatic invariance or energy and magnetic moment. The parallel energy is converted into perpendicular energy, at which points the particles reflect. So it reflects off this, it goes over to this side. Again, non-uniform magnetic field. Alternatively, the parallel motion is decelerated by the repelling force of an increasing magnetic field. Like, interesting. So it's a non-uniform. It might be stronger over here, and pushes it outward. So again, I'm just trying to infer from this, and for future reference. And if you're an expert on this, let me know any statements you want to clarify. So here's another setup here. So mirror reflection of a stronger magnetic field in a magnetic field which converges to the right. Interesting. So I think it's like a magnetic field that's converging all the way here and getting super, super strong. So then it repels that electron beam or something. I'm assuming that's what it is. Note that the guiding center axis of spiral of the reflected beam does not coincide with that of the incident. So note the guiding center axis of the spiral does not coincide with that of the incident. This is due to the gradient and curvature of drift in a non-uniform field. So it's actually, I think it's saying that this does not align with this axis right here, and this separates. I think it cuts off there, but again, I'm not 100% sure what that means there, and so forth. Anyways, I might review it later when I upload the sections video of this. So I go further for figure. This is figure 10, figure 11. So again, I should include this because this is a pretty epic electron beam movement, and again, you can see that trochoid motion there. Figure 11, multiple reflections of an oblique electron beam in a mirror magnetic field. Mirror magnetic field. Okay, this one's interesting. Mirror magnetic field. I think that's the whole key there. I've never heard about this in my life, so I'm going to Google this. So we're doing live research right now, guys. Magnetic mirror. Magnetic mirror. Particle motion right here, and then current, and then basically, this is, I'm not sure how it's mirroring. Again, I just want to see one more setup here. So speed is no longer parallel to magnetic field. So it goes like this. Yeah, initially it's parallel, and then it's, yeah, I think it's like condensing here. So now it's not parallel. Now speed is no longer parallel, so it's condensing it. So that's amazing stuff there. So I think it does make it a different, right? Let's go right here. Magnetic trap. So again, I've never heard about this. A magnetic mirror, also known as magnetic trap or sometimes a pyotron, is a type of magnetic confinement fusion device used in fusion power to trap high temperature plasma using magnetic fields. The mirror is one of the earliest major approaches to fusion power. Okay, interesting. Now we're dealing with magnetic fusion. So it basically has different strengths across it, I think. Okay, so I will have to review this later there. The mirror effect only occurs particles within a limited range of velocities and angles of approach. All right, I'm going to read this right here. So in a classical magnetic mirror, a configuration of electromagnets is used to create an area with an increasing density of magnetic fields at either end. So you basically have super strong at either ends. With an increasing density of magnetic field lines at either end of the confinement volume, particles approaching the ends experience an increasing force that eventually causes them to reverse direction and return to the confinement area. So basically it's like, it's literally a magnetic mirror.
Magnetic fields can be used to confine electric charges in motion to certain regions of space through two primary mechanisms. First, magnetic charges tend to spiral around magnetic field lines, and the net travel of the charge tends to be along those field lines. Second, in a region where magnetic field lines are converging, there will be a component of magnetic force away from that region. This produces an effective magnetic mirror, which sends the charges spiraling back from whence they came. A simple magnetic bottle can be produced by two magnetic dipoles, shown here as two coils. Electric charges can be trapped in the region between these two coils. A toroidal magnetic field can also trap charges by keeping the charges spiraling around the magnetic field lines. This is a simplified version of confinement used in plasma and nuclear fusion research projects like the International Thermonuclear Experimental Reactor. The Earth's dipole magnetic field can also provide a magnetic trap for electric charge. The charges spiral around the magnetic field lines, traveling north and south. The convergence of the magnetic field lines at the poles serves as magnetic mirrors. The net result is that the charges tend to be trapped in a band around the Earth, forming the Van Allen radiation belts.
Here's a hollow piece of straight plastic tube. It's wrapped with electrical windings that create the magnetic field. We pump most all of the air out. Then we inject our fuel into the tube, apply an electrical potential and a magnetic field. This field forces the charged particles toward the center of the tube, creating a small diameter plasma about the size of a garden hose. To prevent the particles from escaping out the ends of the container, we place strong magnetic fields here at each end. These strong magnetic fields act as mirrors. As the particles approach the ends, they face a more powerful magnetic field than the one in the middle. This turns them around, and they bounce back toward the other end in a kind of ping-pong fashion. We call these devices mirror machines. Despite all these considerations, some particles do get lost out the ends. Now, we can design a device that has no ends. We can turn the ends of this tube upon themselves to form a circle or donut. We call this shape a torus, and many research bottles are of such shape, including tokamaks. Theoretically, now the particles should race around and around until they hit some other particles and fuse. Well, it's just not that simple. As fusion researchers have painfully discovered, when we turn this straight tube into a torus, you run into yet another problem. We've compressed the magnetic lines of force much closer together on the inside of the torus, making the field much stronger here on the inside wall than on the outside wall here. Since particles always seek the path of least resistance, they will drift across the magnetic fields toward the outside wall and be lost.
So multiple reflections right here. In an oblique electron beam in a mirror magnetic field, the cyclotron motion is the fastest periodic motion, followed by the slower bounce motion between the mirror points. So there's the cyclone, it's super fast, and all of a sudden I think it bounces off here, and bounces off that magnetic mirror there. And slower bounce between mirror points. Gradient and curvature drifts causes a third slowest rotation azimuthally around the mirror axis. This is the classical charged particle motion in the ionosphere in Earth's magnetic dipole field. Collisions and other scattering processes diffuse the beam. So this is the setup what you see in the when charged particles are in the ionosphere in the Earth. You're going to see those northern lights and so on. And I'll talk about that in a bit. So again, this is a lot to digest, which I will do in a future video or live stream. Okay, so here's another setup here. This is the last one, figure 12. Electron beam injected into a non-uniform magnetic field with a null line. So I think a null line has no magnetic field there. I'm gonna say I'm gonna ask Grok right here. Okay, so here's Grok. So non-uniform magnetic fields with a null line. What does this mean? Okay. First, a magnetic field with strength that varies in strength and direction across space uniform contains a specific line or region where the magnetic field is 0. So that's what it was. Yeah, so the null line basically 0. The null line, the beam meanders along a magnetic null line pointing diagonally down to the right. So you have a line like this that has, I think that, is this what it means? It's meandering it, whoops. Yeah, I think it means like, whoops, again, it's doing that. Yeah, so I think it's going like this. Is that where it is? Again, if they drew some lines that indicate where in the world is this null line. Diagonally down to the right, note the reversal of the cyclotron rotation as the magnetic field reverses to either side of the neutral line. Such meandering and figure 8 configurations have been studied theoretically in the problem of magnetic reconnection occurring in the magnetosphere and then on the sun. Interesting. So then you have a point of no magnetic field right here. It loops around like this. And where does it go? Beam meanders along. It meanders along a magnetic line. So, but then where's the magnetic line like that? So then, where's the magnetic? It's going down to the right, pointing diagonally down to the right, But where in the world is it? Is it up here? All right. Anyways, this is for future study. Hopefully, you enjoyed this reading up in there. I'm going to read a bit more. This is first. Here's an amazing charged particle in a magnetic field 3D calculator from that Tom Walsh made in GeoGebra. So this one made it. This is in a magnetic field. There's no electric field in this, so it just loops around in a circle. So I think the electric field will cause it to drift in that area, in a specific area. So if we go back here, this one here. So the magnetic field, this one here, so it's drifting across to it, and then it's moving it, but it's pushing it this way, and then yeah, it's basically going towards the magnetic field, but the electric field is pushing it, and then as the again, I'm not 100% sure how this all works, but anyways, so here's a setup right here. So if I press play. This is a magnetic field, and it's going up. Yeah. Oh, whoops. This is a play. Okay, there's a play. It's going in a loop like that. And if you show magnetic field is going up. So this is a particle going in it like that. You could change this setup here. The stuff here, you can change the animation speed. This is the B setup there, the M, and other show velocity. And you can also show the velocity here. This is show magnetic field, show particle path. And then reset. Let's see the reset. Then there's the arrows like that. So there's the arrow of the velocity vector. Anyways, so that's that. So it's pretty cool. Want to include that. And note that a moving charged particle experiences what's known as a Lorentz force from a magnetic field according to the right-hand rule. Here's a video on that path of charged particle and magnetic field, moving charges and magnetism. So this one is pointing into the page. Yeah, so I'll draw this with a white line, or actually, I'll draw this with a blue. Yeah, okay, so that's a blue. Yeah, so this is going into the page. So this is pushing it straight down. And what happens is you use your right-hand rule. You curve this in the direction. You point your fingers down. So it's pointing down into the direction. This is going straight down into the direction of the magnetic field. And then the force that this is, I think, a positive charged particle experiences that's moving is going to be to the right. So this is one right here, and this is moving forward like here. Yeah, no, I think the way it works is this. You put your thumb in the direction of the velocity. This is the velocity of the charged particle. And then you curl your arms in the direction of the magnetic field. So in this case, it's going into the page. And then using your right-hand rule, the thumb pushes this sideways. So pushes the force sideways. And then if you keep doing that, it's going to go around in a circle like that, in a circle around this. This is just a magnetic field. Let's see further. And then here's some more stuff right here. So here's illustrating it more. So as it and then as it turns, so particle goes in a circle. So v is perpendicular. The velocity vector is perpendicular to the b vector, and the q is the amount of charge, and this the v is the velocity in this magnetic field. Is a cross product using it. And as it goes here, you're always going to turning your hand, and so it keeps going in a circle. And then in general, this one is and this one here is in a helic one. This is going at an angle. This is a magnetic field going perpendicular to it, but there's no electric field. This one, but if it goes at an angle, you're gonna have it going in a loop like that. If it's starting off at an angle. If it's just starting off initially as like that, then it goes. If it's starting off perfectly perpendicular magnetic field, it goes like that. And then it goes further in general helix path, just because not everything goes perfectly in line with that magnetic field. And then the Earth's magnetic field is like this. So then the particles get trapped in, it goes in a cycloid and gets trapped in these areas, and that's where you get these northern lights typically show at the poles. So yes, that's fascinating stuff there. And here's another video, right-hand rule video. Another way you can look at it, you can have the velocity vector pointing with your finger, magnetic field pointing down, and then this going up, and then the force is your thumb. So you can do that as well. And here's another illustration. This is from Wikipedia. And the link to the Wikipedia one right here, I think I put a link. This is a Lorentz force right here. So that click that link there. These are the images. So if you have magnetic field here pointing out of the page, a velocity here. If you have Q, a charge right here, if its charge is positive, it curls like this. If it's negative, it goes opposite way. So if it's your thumb, I think this is for positive, and then the negative would be just going downward. So curls up like that. And if it's 0, if there's no charge, it goes straight. So trajectory of a particle, the positive charge or negative charge, Q under the influence of magnetic field, which is directed perpendicular out of the screen. Hence this arrow pointing up. And here's another setup right here. Again, I told you this would be an extensive electromagnetic setup here. A deep dive. So beam of electrons moving in a circle due to the presence of a magnetic field. So here is a beam of electrons moving in a circle. Yeah, this one here, beam of electrons going in a circle. The magnetic field is going perpendicular to it. Purple light reveals the electron's path in this teletron tube. It's created by the electrons colliding with gas molecules. Again, if colliding with it, that's the light that's getting excited and emitted outwards, as I went over in that previous paper or previous article. So here's another. I'm gonna simplify. Go lower here. So here's a charged particle drifts in a homogeneous magnetic field. So A is no disturbing force, and then B is with an electric field. Let's go right here. So this is A. Where's the A one? There's no A. Oh, yeah, there's A. There's A right here. So here is, this is the magnetic field, pointing out of the page. So, magnetic field points upwards through the page. It's basically pointing out to you. Alright, so it's pointing out, to you. Make this back into black. And, so if you have a negative one, it spins this way. If you use the right-hand rule, so if it's initially starting off, I think it's like use the right-hand rule, the thumb. Yeah, I think this is it's got magnetic field like this. I'm trying to illustrate this. Alright, yeah, here, I think I got it. So I'm going to use this right here, this setup right here. So if you have your thumb, yeah, the thumb is the force, but if you have your index finger, I'm going to see if this right here. So this looks like that. And this is going in this is the initial direction. So if this is the path of it. And then your middle finger is going like this. This is your, and this is your rest of your fingers. Yeah, this is your other 3 fingers, like this. And then your thumb, would be sideways. Yeah, this is your thumb. Yeah, alright, this is the thumb. So in other words, if this is going up like here, that's the velocity. The magnetic field is pointing out right here. So in other words, the thumb is going to point to the right. So this one's going to go to the right and loop in a circle. But then if it's a negative, it's the reverse setup here. So in other words, if it's going this way, then it's going to be rotating this way here because the force is going to be acting on the other side. Again, hopefully you grasp that, and that's just right here again. That's just right here, and then reverse it with your left hand. All right. So anyways, so this loops out around in a circle. Charged particle drifts in a homogeneous magnetic field. A, no disturbing charge, it just loops in a circle. B, with an electric field. Yeah, so let's look at B, what happens with an electric field. So if you have an electric field going down like here, this one's going up. Yeah, so now it's going to be, the positive one will loop like this. So it's pretty fascinating. And then a negative one, if a negative charge will be going, let's see, yeah, instead of looping up like this, it's looping down. Yeah, so these are both drifting on this side, and it's going to go like this. And this one is going up. So basically goes opposite direction of that. And then if you have, what's another one? With an independent force, after this is gravity. So if you have gravity going down, So this one's pretty cool. So this one, and if you have gravity, and it's the same thing. But this one is going the opposite direction. Okay, this is going opposite direction. Interesting. So drift is going, if you have the gravity's going down, it doesn't reverse the peaks like that. It just goes in a different direction with the force of gravity there. And now going further in an inhomogeneous magnetic field or gradient H. So if you have a stronger field going up, so if you have basically you have pointing a magnetic field super strong over here, so super strong and then super little right here. The setup is similar to gravity. All right, so this is identical. So gravity is gravity right here. Yeah, here I just want to write that again. So is gravity just a magnetic field gradient? Magnetic field grad. Unbelievable! I think we just solved this right here. So it's pretty interesting here. It looks exactly the same setup for the charged particles. So yes, fascinating stuff. Anyways, that's something to think about. And here, MES note, is gravity just a magnetic field gradient? All right, I know, it's just observing it quickly, but yeah, I think it's I think it's something more than just that, but I definitely think they're connected in some ways we're not being told. Anyways, it's epic stuff there.